Good morning, everybody. We're happy to have Simon continuing with his second lecture.
Good morning, everyone.
Is it on?
It's supposed to. So good morning. So let me start with a quick recap of where we finished last time. So yesterday we talked about this idea, this notion that in nature doesn't seem to be any instantaneous action at the distance. And we talk about how that idea explains a lot of things, like this, that all forces are mediated by fields, particles, why we can draw Feynman diagrams to understand forces, and so on. And we talk a bit more quantitatively about a specific process, which was the exchange of a massless spin 2 particle between two scalars. And here, see, spin 2 in the middle. And we saw that this kinematic statement was essentially equivalent to saying that this amplitude at the pole that had some coefficient that turned out to be 32 pi g Newton over q square. Q is this momentum times something that was p1 dot p2 square minus 1 over d minus 2 p1 square p2 square plus terms with no pole in that channel. And we saw how that formula, when you took its relativistic limit, gives you the correct light bending around the sun. So what I want to do today, so I will actually make a few more comments about the interpretation of this calculation. And I want to spend a bit more time today on, after discussing with some of you, I think it would be very appropriate here to spend time on this general question, on this general classification program of what interactions are possible. So I will try to highlight some of the ideas, but also the limitation of these ideas, of this sort of S-matrix approach to understanding interactions. And a lot of what I will discuss has appeared in the past in lectures, for example, by Nima Kaniamed over the past 15 years. But as far as I know, there's no written clear summary of that you can find. So it has value that I go through it in this forum. And the next thing we will do, probably next time, we'll actually go into the analyticity and dispersion relation. So that will actually be for next time. Okay. So I'd like to make a few more comments about this calculation. Okay. First is a very, very general one. So just to recap what the key point was we basically use this linear classification, which is that the particles are labeled by E rep of the little group. And this is why we add this trace subtraction, because if you don't subtract the trace, you don't have an E rep of SOD minus 2. That's a minus 1/2. And that minus, in D of work 4, that minus 1/2 was responsible for the fact that the deflection angle in GR for a photon divided by the Newtonian prediction was this famous factor of 2 that we finished with. Okay. A general thing we can say about this formula also, that you can ask, what if I exchange a particle of spin j instead, massive or massless? Then what you will find is that the vertex, now the thing you exchange will have, say, more indices, And the thing at the vertex it will couple to will have more powers of momentum. And therefore, when you exchange a particle with spin j, you get an amplitude that grows like s to the j. Okay? Implies that m goes like s to j in the rigid limit where you take s large and not the other ones. Infinity and error impact parameter or momentum transfer fixed. Okay? So this is a very kinematical thing. That's very clear once you start writing down Feynman rules. And there's a thing that I want to quickly mention, that this sort of logic historically has been fruitful to reverse it. And when people say that when you see an amplitude that behaves like a power law, S to J, rigid theory tells you that you can understand this as exchange of an effective excitation of spin J. J. Effective excitation, effective particle. And this sort of a kinematic statement you can make even in the power is non-integer. So for example, a lot of the physics in soft QCD can be understood in terms of a so-called pomeron, which is effective spin 1.08. It gives you an amplitude that grows at a certain rate. Okay. So people use this language. Spin of the exchange particle is really just a proxy for the power law growth of the amplitude. The other thing I would like to mention that's specifically about this, either way, yeah. This, here I'm using the word soft in the same way that Sasha has been using it yesterday. And you may wonder, why is it called soft? Because S is very large. Yeah, this is, it's called soft because this is for T much less than lambda QCD square. So, and you can ask, for example, you can ask in this physics of forward scattering. So this is very high energy forward scattering. You can ask in this physics, do we need alpha strong at the scale S or alpha strong at the scale T? And it turns out that you're sensitive to physics at the scale T. So it's really why the word soft is appropriate. The lowest scale, the most infrared scale actually dominates the physics in this rigid limit. Yeah?
I'm having trouble seeing why this for the graviton when it goes like S squared.
Yeah.
This rigid limit.
Yes. Yeah, so.
Could you repeat the question?
Yeah, so not sure actually answers the question. The question is, why does it go like S squared in the gravity?
Yeah.
Yeah, so maybe one thing I can say here is that, okay, it's a bit of the definition of massless spin 2, but the fact that it goes like S squared means that remember that to get the phase shift, we needed to take the amplitude and divide by some relativistic factor, 2e1, 2e2, times some velocity difference. And after you divide by this kinematic factor, you get a force that goes like S to the j minus 1. And so this is a statement that gravity couples to energy. The force is linear in S. Okay? So that's why it might make sense that for gravity you have spin 2. Okay? Yeah. So the specific calculation we describe for gravity is let's just describe a bit the regime in which it's valid. If you look at the dimensionless parameter of this gravity amplitude, is basically 2. There's something that is the magnitude of this phase shift they calculated last time, which go like g Newton times the product of energies divided by b to the d minus 4. And that's a dimensionless parameter. And the other parameter is a scattering angle that goes like g times some energy divided by b to the d minus 3. They're a bit different scaling. And if we make a axis of different energy scales at some large impact parameter, the sort of story is the following, is that at relatively low energies, this phase is still small, and the amplitude we calculated is really the right answer. So we have S of S comma B approximately equal to 1 plus I delta. This is called the Born regime, because you just exchange one graviton. It turns out that the next thing that happens as you increase the energy is that this phase, this tree-level thing, just exponentiates. So you get so-called iconal regime, where you get S as a phase. So this is the first term. Then you keep going up. Eventually, you get tidal effect or inelastic effect, emission of gravitational wave, and so on. And this is when the magnitude of the scattering amplitude, the probability that you survive, gets less than 1. So, and then eventually, you have black holes. If you fix the impact parameter and go to very high energy, eventually you make black holes. Okay, so this storyline will be will be discussed much more at length in Sebastian Misera's lectures. And here I just want to say that the calculation we did yesterday of the deflection angle works up to here. So this, essentially, this exponentiation was perfect. We basically said that the deflection angle was a derivative of the phase shift, and saying that the momentum transfer is S dagger d over dp, sorry, d over db of S. That was valid up to here. Okay. So our calculation does work even for classical objects where the iconal phase is huge, but the scattering angle is not large.
Question?
Yeah.
What does chi mean?
That was the deflection angle. All right. Yeah. And also notice that the large B expansion is similar to is equivalent to the small G expansion. So that's why we can really do perturbation theory. Yeah.
So the large B expansion, what do you think as a black hole? Because there's no causal structure here. So what do you characterize as a black hole?
It's the production of a black hole in the intermediate state. So you're taking two particles, boring scalar particles. You have a huge energy of m, and if they get within their Schwarzschild radius, they will create a black hole.
There is a causal constraint.
Yes, but the elastic amplitude will not really see it, but the black hole will show up as an intermediate state in the amplitude.
This is large energy and also large B, the direction of the arrow.
B is fixed. In this arrow, B is fixed.
B is fixed. I see.
Thank you. Okay. Okay, so now I want to go to this first pass at understanding what theories work. Okay, so now we said that mass spin 2 implies some prediction of Einstein's theory. I want to say a bit more. I want to go a little bit more in that, and we'll talk about the soft analysis by Weinberg. And we'll talk about the results and limitation of this. So this will have some overlap, I believe, with Anna's lecture. But yeah, so I want to discuss a bit the output of this old program, because it's a bit foundational to what comes next. Okay. So the idea here is to understand what happens when you have some radiation of soft particles. And that will also tell us a lot about long-range forces. Okay. So the first step is to understand the soft limit of vertices. And so on-shell vertices. We see in a second why that's all that matters for this analysis. So now we did it for a scalar last time, but in general, we can imagine you have two different flavors where this index A can have a flavor or a spin. Okay, so now I'm scattering some spinning particle. It could be massive, massless, against some gauge field. I would start with a vector field, and there one can play a game and try to understand these vertices in terms of the various invariants you can write. And these are functions of, in general, they are functions of the polarizations and the momenta of this particle. But remember that we're on shell, so because pi, remember this density last time, that all the dot products between p's can be expressed in terms of p squares, which are constant. So this is really just a function of the mass square. Could be different from the two guys. And it's a function of, basically, you could have polarization. You could have E dot. It's basically a function of these things. And yeah, here, and if you look at the literature, when you start doing calculation with this thing, you can use either open indices, with say the polarization as index mu, or you could dot it into polarization epsilon mu, like you do in textbook. So one can go back and forth from this notation. Here I would keep the open index here and the epsilon polarization for the particle you're scattering it. So you could have that, and you can have p mu. So we can have these sort of structures, and it's a polynomial in these things. So one can just enumerate this polynomial and find the one that are gauge invariant. Okay, so it's a bit of a game. And what you find is one of the exercises in the question 1 asks you to do this for photons. But you find in all cases is a finite list of couplings.
Just to be clear here, we can't just do this around momentum transfer 0?
You can do it in general. It's always a finite list of coupling because we're assuming q squared equals 0.
Yeah, that's what I meant. Yeah, good.
Yeah, exactly. So if you drop q squared, then it's a finite list. Yeah. And the thing that where you don't drop q squared, give you things that you could redefine to give you like 4-point interactions and so on. So the genuine 3-point interactions are the property. Yeah.
Where does the polynomial assumption come from?
Well, the polarization are just sort of placeholders for spin, so you can't really put the polarization downstairs. And then there's nothing else you could put in the denominators because all the pi.pj's is constant. The only thing I could have in the denominator are the masses, because everything else involves the polarization on the momenta and some indices. Everything else has some like index.
So why is pi.pj constant?
Because you can express it in terms of p squared, which is constant.
Squared, which is 0.
Yeah. Yeah. Exactly. So yeah. So the momentum square A are either equal to some square or 0 from this guy. Thanks. So you can do this analysis, but the thing that you do a shortcut, and the thing I want to discuss today that's relevant for this soft analysis is that when you take the limit as q goes to 0, and then you cannot no longer, this polynomial can no longer use q. So the polynomials you have to use p, and there's really not a lot of things you can write down with p. So basically, there's just two options. So if you have one option. So if you have a spin 1 particle, the only thing you can get is some coupling. Let's call it EI times pi mu, or that's for spin 1 soft particle. And if you have two particles, you can have pi mu, pi mu. Okay. All of these plus order q to the 1. Okay, so the soft limit is always very simple. There's nothing else it can be than it's measuring the momentum of the thing. And this multiplies a Kronecker delta in flavor and spin. Okay, so in the soft limit, you never change the identity of the particle you're scattering. You're just measuring just a vertex is proportional to its momentum. Okay, there's really nothing else you can write down this limit. So you need some momentum transfer in order to change the identity of the particle. Yeah.
Can you write this a little bigger?
Okay, yes. Yeah. So here I wrote the vertices is E times P times Kronecker delta ij. And I will try to write bigger for the next things.
Sorry, Simon. Even if you're not in the soft limit, if you write a q mu, shouldn't that go to 0 because the epsilon is
Yeah. Yeah, Q mu goes to 0, but
no, sorry.
yeah.
When you dot it with the epsilon.
Yeah, Q. When you dot this Q against this epsilon, this is not 0.
Oh no, I meant the other epsilon.
Yeah, that one here, that gives 0. Yeah.
So that you shouldn't have a q mu, right?
Yeah, exactly. This polynomials are defined modulo Q mu. Yeah. Thanks. Yeah. So once you have these on-shell vertices, we can analyze a soft limit of a general amplitude. And this is for spin 1, this is a standard textbook presentation. But for spin 2 and so on, it's less discussed. So I will let's do this. Let's do them together here. So you write down some complicated Feynman diagram, and you tack on some soft particle. The question is, what's the leading behavior you can get for this amplitude with one extra soft particle? It's a useful question to ask because it will tell you how many soft things you radiate in this process. Okay? It's a very natural question to ask. That's the starting point of this Weinberg analysis. So what you find is that suppose this particle here is momentum pi. What you find is that the important thing in this analysis is that this propagator here will have a 1 over pi plus q square plus mi square. But as you take q to 0, the term with p squared plus m squared cancels because this guy is on the mass shell. So all you get is 1 over 2q dot pi, which goes like 1 over q. So whenever you insert a soft particle on an external leg, you get this 1 over q factor. And the numerator doesn't have any q, so that's a 1 over q effect. But whenever you insert this guy on the internal propagator, you don't get this enhancement because the internal propagators are on shell. So this is only for external propagators. And that allows you to directly write down what's the soft limit of the amplitude. So the soft amplitude with one extra soft photon, for example, as q goes to 0, we'd go to the amplitude without the soft. And as q, since q is going to 0, the momentum conservation is still respected, times basically a sum over all the external legs of the charge. We have this vertex here, pi mu over pi dot q. This is for spin 1. And for spin 2, you get a similar things, but now you get kappa I, pi, mu over pi dot q. This is for spin 2. Okay, so this is a famous Weinberg soft factor, and this is the same thing for gravity. And all of both of these are valid up to order q0 terms. These factors have a lot of very nice properties, and I'm sure they will appear a lot in. You will see them also in as lectures. But let me say what is relevant to Weinberg analysis here. So remember that the polarization of this guy has to be in the SOD minus 2 polarization. So it has to be orthogonal to Q, and it has to be that when you take a polarization that's along, there is null polarization along Q that must decouple. So if you require that Q mu dot mu equals 0, you get some interesting constraints on these couplings. So if you require that, you get the constraint that sum over all the particles of EI. Notice that when you dot into Q, you cancel this denominator. So you get a clean sum of EI equals 0. Or for gravity, somewhere I of kappa I pi mu equals 0. Okay? Maybe it's a new index there. Okay. So this is a very simple interpretation. It means that if you have a photon, if you have a massless spin 1 particle in your theory, the strength of its coupling to matter you define to be the electric charge. And this is saying that electric charge has to be conserved in any process. So this is charge conservation. And this is the momentum conservation. Okay? And well, actually, for it to become momentum conservation, you need all of the couplings to be the same, which is the kappa I equal kappa. So from this analysis, you see that, and this has to be true for any configuration of the amplitude. So you see that, like, if the kappas are not all equal, this becomes a constraint on the momentum of the things you can scatter, which is weird, which doesn't make any sense because the momentum of the things you scatter are free parameters. So in order for this to be true for any p, you need this to be proportional to the momentum conservation, which means all these kappas have to be the same. Okay? So that is the universality. So this is how Weinberg explained that if you have a massless spin 2 particle, it has to universally couple to all matter with the same strength. So that's the universality of gravity. So anything that can interact must probe the same gravity. It's a very powerful result. Yeah. Yeah, exactly. In field theory, you derive it from the word identity. And here, this is needed in order to decouple the null states. Zero norm state. Because Q mu is null vector, so there's a polarization that has zero norm. That's better do nothing. Okay. Something else which you can say is that if you extend this analysis to higher spin, if you have a spin 3 or higher, then the same constraint will give you a sum. That sum, let me call it kappa I prime times pi. Say at spin 3, you will have 2 extra p's times indices. And this is a bit like asking for some higher spin conserved current to exist. But this really is too strong a constraint on the external momenta that you're scattering. This cannot be satisfied if you have interactions. So that implies kappa I prime equals 0. So what this shows is that if you have a higher spin massless particle, it cannot interact to matter. It cannot do anything. It cannot interact. Or at least, more precisely, it cannot interact to this leading term in this low small q expansion. Okay? So higher spin particle cannot interact to leading order in q goes to 0. Okay? So it's analysis of the soft limit, and you learn something about the possible soft limit of interactions. And for higher spin, nothing can happen. Okay? Yeah.
What does it mean that they can't interact to leading order? I would have expected it without in the soft limit.
Yeah. Yeah, that's a very good question. So the question is, what does it mean? How could they interact beyond this leading order? And I can give you an example that is a little bit, but it works at the level of gauge invariant constraint. It works. And the way you can trivially satisfy all of the gauge invariant constraint is the, I would just write an analogy in QED, is if you assume that all of the interactions of this particle are proportional to some kind of field strength. So this would be like in QED, where you have a photon that coupled to, normally a photon will couple to something like this. Now you can say this, let's say this is not there. But the next thing you can write down is some coupling, E prime times F mu nu, let's say with gamma mu times psi. So if all the interactions are made from things like this, then you will satisfy the constraints. But you don't get very interesting long-range forces from that. But this is the thing you cannot rule out from gauge invariance. So the analog of this for higher spin is still allowed by this analysis. We only have things that are explicitly function of field strengths. Okay.
Sorry,
Yeah.
the point that when you allow for these kinds of interactions, the polynomial that you suggested for the vertex gets more possible contributions from
Well, it's still part of this finite classification. And typically, it's only going to be the term with the maximal power. So in terms of dimension analysis, this is very unnatural. It's only, you're fine-tuning all the coefficient to 0 except the thing with the maximal number of derivatives. Yeah. So let me make a few comments about analysis. Let's return to spin 1 and spin 2. In these cases, a bit more is true. You don't just have the leading soft theorem, leading power of Q, but subleading is actually universal. So I want to make a few general comments, because this analysis also tells you things about loops and things that go a bit beyond tree level that are important for the general applications. So one thing that is true. So one thing that is true is that you have subleading soft. So you can go to the term of order Q to the 0 is also predictable in QED. Or M up to Q1 in gravity. And what happens here is that they factorize. Meaning that you can write these terms in terms of something acting on the amplitude without radiation. So factorization means that you start from the amplitude without radiation. You can tack radiation up to some accuracy in small q. You can predict all of that. And the rough reason for this, the intuitive reason that was used, this is our very old results, is that the first gauge invariant local thing you can write down is a field strength that goes like q to the 1 in QED and q to the 2 in q square in gravity. So up to q1, you cannot write anything at the interaction point. So they factorize, but they also are theory dependent, because they depend on the details of these. So if you have higher order correction, higher derivative corrections to your theory that add this order Q1 correction to your 3-point vertex, these will show up in these guys. They're non-universal, but they are factorized. Another thing that is worth mentioning is that for loops, loops have been very well studied. And so in Yang-Mills theory, for example, at one loop, you have graphs like this, which go like, which can couple more than one source. So you have one soft gluon that is sourced by 2 charged particles. And that would go like some kind of G cube or times Q to the n over Q to the 1. So it has the same power in Q as a leading soft theorem, but it depends in a more complicated way on the external things. Okay. At 3 loops, you can have things which couple more and more partons. So the so-called soft current becomes more and more complicated as you increase the number of loops. Okay. In gravity, the analogous thing, because gravity is dimensional full constant, would give you something that go like g times some energy square. Leading behavior will have a 1 over q. And here you add a q to the d minus 3. So you get subleading powers. So all of these loops in gravity give you subleading powers of q at small q. And these have been very nicely analyzed in work by Sen and collaborator in the past few years. They have these classical soft theorems that effectively calculated loops using classical techniques, and you can predict various tails in the soft graviton spectrum. Okay. Yeah, the other thing you can do is that people in QCD, you can take two gluon soft and things like this and so on. You have multi-soft factorization and so on. So all of these so-called soft, so if you want to read about this, the keyword to search for is soft currents. And they are very important in the in PQCD calculation. Because when you calculate a cross-section in perturbative QCD, it's very important to understand the phase space to irradiate multiple soft things. Okay, so there's a lot of understanding about these things in this literature. So I want to move toward more bootstrap-like topics. And what we learned from this analysis, you see it's all from this Weinberg analysis about the soft limits. In order to go beyond that, it'd be useful to look at 2-to-2 scattering. So I want to move now to constraints from 2-to-2 scattering. To give you a flavor of this constraint, the paper by Arkani Ahmed, Huang, and Wang that I mentioned yesterday is a good reference for this analysis. So the basic question is, okay, we had an argument here based on soft limit, that the universality of couplings, but I'm going to give another argument. Why? For example, the coupling of gravity to a photon is equal to that to a scalar, equal to that. Okay? And the way this other line of argument, the way it will work is that, well, in principle, right, for example, the thing you would like to know is what's the force between a photon and the sun. You have a photon, sun, photon. The graph you would like to calculate is this graph. And this is imminently observable, like bending by the sun. But the thing we'll actually study to constrain it theoretically is we'll study separately the scattering of a photon against a graviton and a photon or graviton against a scalar. So graviton scattering is a tough experiment. It has not been we measure one graviton from interferometry, but graviton matter scattering is beyond what we can detect. But it's actually a very useful, tough experiment. So let me explain the line of tough, starting from gluons. Suppose we have many spin 1 particles. So then, when you look at their couplings, and you put an index A here, you could have some structure, let's call it TAIJ. There's some matrix that will describe all these different spin 1 particles coupled to different type of matters. Right? So just introduce this abstractly as a matrix. Okay? And now we're going to study this process where we scatter many of these spin 1 particles against matter. So this could be I, this would be J, so this would have flavor K, this would have A and B. And this is a photon, so it has index mu and nu. Let's call this guy Q1, this guy Q2. Okay? In principle, you can imagine two graphs like this. And what happened is that now the reason these processes are a powerful way to constrain interactions with involving spin 1 particles is that now the spin 1 particle is on the outside. And therefore, you can ask the amplitude, it has to be that this null state decouples. So it has to be that this amplitude is orthogonal to Q1 mu. So we again impose that Q1 mu times M mu equals 0. That has to be exactly satisfied, not just at small q. And what happens when you try to solve this identity is that the q dot the vertex gives the unchanged mass shell condition, which is satisfied on this leg, but it cancels this propagator. So we get kind of word identities that cancel this propagator. So these two graphs get to talk to each other. But from these two graphs, basically you get a product of you get a product of TA, TB with external leg I and J. This product of these two matrices from this graph. And for the other graph, you get the other thing, TB, TA times IJ. So if you have abelian-like couplings that commute, you're done, and this is satisfied. But if these matrices don't commute, this does not work. So the particle physics philosophy is that when you have a problem, you invent a new particle or new interactions. Solve it. So problems in amplitude have to be solved by new interactions. And what will solve this problem, in this case, is that you can add a third graph. If the spin 1 particle has a self-interaction, now it's possible to cure this problem. Let's call this vertex FABC, just to give it a name. This has C. And this is A and B again. And now, again, you look at the word identity. It will cancel this propagator and give you things which all have the same momentum structure. But now it has a structure that has FABC times TC. And also, all of these graphs add, in principle, some coupling G. And this could have been a G prime. And what you find is that, and this has to be equal to 0 if that's the physics which solves the problem. So what you see is that if you have a massless spin 1 particle, if you have many of them, the only way you can constantly couple it to matter is if at the coupling satisfy a Jacobi identity. Okay? So basically you need all the couplings to be the same, and you need TA, TB to be IFABC, TC. So it has to be that you can write this coupling like this. So you learn that the interactions for massless spin 1 particles are associated with Lie algebras from this sort of argument. Yeah, there's a question. Yeah, it's again very important, is because this represents a launch null polarization. So this is like having a launch polarization of a photon that is epsilon mu equal q mu. But this launch null polarization has 0 norm. But we expect that the particles live in some Hilbert space. So if you have a state, if you have a state in your Hilbert space that's a particle with this polarization, a photon with this polarization, it's a null state. So a null state should not do anything. Otherwise, you have a problem with probabilities and probability of conservation and so on. Okay?
So that's like, as long as you have a soft particle, you want to impose this convention.
Any gauge particle. It doesn't have to be soft. Any spin 1 particle, its polarization needs to satisfy that. Yeah, its amplitude needs to satisfy this constraint. Any spinning particle needs that. Yeah. So basically, what we learned from this is that if you have a spin 1 particle, the interactions are associated with Lie algebras. Okay? Which, of course, we knew because Yang-Mills, but that's how you see it from this. Okay? you ask it again?
To say that spin 1 implies Lie algebras, but I think the FABC did we not put in by hand there?
Yes.
We would have to show that there are some antisymmetry properties or something in that, that vertex.
Yeah, so I think it follows from this constraint, but it also follows from one has to do a little enumeration game here. When you enumerate the structures, when you play this game of enumerating the vertices that you can have between 3 spin 1 particle, you find that the first thing you can write is antisymmetric in momentum and polarizations. And therefore, if these spin 1 particles are bosons, this FABC has to be antisymmetric. Thanks for the question. So for gravity, the same analysis tells you similarly that you can't have just a spin 2 particle coupling to matter, but the spin 2 particle must self-interact for spin 2. So if you have matter and you couple the graviton to it, you have these graphs. And in order to cancel, in order for the amplitude to be orthogonal to Q mu and decouple this null state, you need this graviton self-interaction. And this interaction, in principle, came with some. The first thing you can write down turns out to be fully symmetrical, and comes with some coupling. Let's call it kappa of gravity. And in order for it to solve the problem, you also need that the coupling of graviton to matter to be the same as the coupling to gravity. The coupling of gravity to matter has to be the same as the coupling of gravity to itself, which we just call the coupling of gravity. Yeah. Typo. Thanks. It was meant to be a same matter leg as for the other graphs. So this argument is actually quite useful because it's an argument that, because it's phrased in terms of 2-to-2 scattering, so we reach the same conclusion as we had before, that the coupling of graviton to matter has to be universal, same coupling to everyone. But having proven it from tough experiments involving 2-to-2 scattering, now we can try to go a little bit beyond this argument and start modifying the interaction of gravity, try to go beyond gravity. So that would be the direction we'll go. Yeah.
What's the motivation behind the matrices not commuting in gravity?
Yeah, here you don't have matrices, but it's basically the thing that happens is that because the vertices have some momentum, what happens is that the momenta here don't line up. So these two graphs, even though they look like they will commute in gravity, they don't cancel each other. So these two graphs together don't solve the Ward identity. Yeah. In some sense, the diffeomorphism algebra is not abelian.
This is a quantum version of principle of being.
Yeah. You could say that. Okay. So this is all good for massless particle.
Quick question.
Good.
For the case of gravity, I would imagine if you start having higher order vertices,
Yes.
we have more couplings in the graviton, like to itself.
Yeah.
In order to fix gauge invariance, like you need to keep adding stuff.
Yes.
For the gauge field, it's like subtracting.
Yeah. It's a little bit. I will say no. So one thing I can say is that the presentation of gravity in terms of diagrams. So of course, if you keep going, so with this line of argument, Weinberg in the early 60s, they show that you keep going new vertices. So for gravity, you need more nonlinear vertices. and really argue that you really convincingly argue that you can get you get full nonlinear gravity in this perturbative expansion. The thing I would say is that what the vertices in gravity look like really depends on the choice of gauge and also choice of variables you use in the path integral. There are some variables which make there actually are variables which make the expansion terminate. I think it's this variable square root of g times g mu nu. If you use this field, it actually makes the expansion terminate nicely. So there are paper by Grant Remen and Cliff Chung on this recently. You can read on. So you know, whether you need infinitely many vertices or not is a little bit of a question of. It's not an invariant statement, but yeah, you do need the claim is that the precise claim is that if you solve these Wardy densities in the minimal way, meaning without introducing a dimensional full parameter beyond G Newton and that will represent aeroderivative interactions, so R will be the unique solution to leading order in derivative expansion. Okay. Okay. But if you allow couplings that go beyond the that have other units than G Newton, you can have more solutions. Yeah.
For this Gothic metric stuff, the price you need to pay is to introduce an auxiliary field with 3 indices or so. It's not.
Yes, that's true. Yeah, maybe it's not perfect. Yeah, doesn't work perfectly, but it does help your life a lot.
No, for sure. But I would say in this analysis, it's not clear to me where that A field would come in. Like, where would an auxiliary field show up in this analysis?
Yeah, you won't really. So by definition, auxiliary field are things which with propagators you can just like they're fiction. You can collapse them. They don't really have 1 over p square downstairs. So they're just graphical aids. So we don't really see them from the mat. Yeah.
So in the spin one picture, we kind of, by doing this coordinated analysis, we kind of think of like, that we need gauge groups or gauge theory, right?
Mm-hmm.
But then here in the spin 2 case, how do we see that like the gauge group of gravity should be like diffeomorphism?
You don't really see it, but you see that, as we said last time, you see that the polarization have this ambiguity, which is a q mu times something symmetrized like this. So you can recognize this as a linearized diff invariance, and then by tracking the things at the nonlinear level, you can see that it's kind of a perturbative expansion. So we can see that it's building diffeomorphisms for you order by order. Yeah. But you have to recognize it. So I want to make a few comments about some limitations of this approach. Yeah. Yeah, that's my next. Good. Thanks. Loop effect is the question. Well, actually, a quick thing I can say about gravity. So for Yang-Mills, this is really, for spin 1 particle, this is really assuming you have a perturbative parameter. So this is bootstrapping perturbative gauge theory. And then using a similar line of logic as Sasha was describing in his talk, unitarity forces you to have loops. Like you cannot have the trees and not the loops. And actually, it's a very practical way to calculate loops that people do in practice in PQC calculation. You use unitarity to predict the cuts of loops from trees and the optical theorem and so on. So we won't go that direction, but yeah, once you have the trees, you're forced to have loops and so on. But the starting point is that first the trees need to make sense. And that's a constraint on the theory. Okay. In gravity, the problem is much less stringent because of the units of, as you see from this formula that I'm erasing, the units are such that the loops decouple in the infrared. So at least you have a large distance expansion where you have full control over the loops. So comments. Okay, I would just say this. So, yeah, from this sort of analysis, also, you can always diagonalize the coupling of. So suppose you had many spin-2 particles. This is a question that appeared last time. With multiple spin-2 particles, you could of course diagonalize the coupling to one of scalar matter. But this argument will tell you that they have to be lined up, so you can only have one massive one massless spin-2 particle which interact with matter. So you cannot have multiple ones. So let's discuss. So this is for massless particles. What happens if you have a small mass? This is a bit less discussed in the literature. For light spinning particle. So generally speaking, then the little group is SOD minus 1. The polarization live in SOD minus 1, not SOD minus 2. And you can think of it in the following. Now the polarization satisfies a constraint. And Q square is minus M square. So basically, the time component of the polarization disappears. So the polarization of a massive particle in this rest frame is just some vector, a spatial vector. But you have a constraint on the polarization. But when you look at the amplitude takes this form. It means that this amplitude is unconstrained. So the amplitude no longer needs to satisfy ward identities. When you have a massive particle that coupled to stuff, the thing that sources it doesn't need to be a conserved current. Okay. Okay, let me not write it like this. So basically, there's in the first analysis of things, there are two cases. Seems to be two cases. You can couple to a conserved current, or you can conserve to a non-conserved current. That, at least in my thinking, I find it useful to distinguish. And it's two cases, but it's really a gray scale of cases. The first case is that it couples to a conserved current. Which basically means that epsilon mu and q mu and mu equals 0. Okay. An example of this case is QED, where you just add a mass term for the photon. So-called Stuckelberg mass term. You can add that to your Lagrangian. It breaks Gauge invariance, but you can actually add it, and it's perfectly fine. Okay, it's a different theory, but it exists. So let's analyze this theory a little bit more. Okay. So the photon nominally now has an extra degree of freedom. It has 3 polarizations, not just 2 transverse ones. There's an extra longitudinal one. Okay. So the polarization, in general, epsilon mu, you can write as either a perpendicular polarization in the 2 transverse direction. And I assume that the spinning particle is light, which means that you should think of it as moving very fast. So it's almost like null. It's almost like massless. So why does it massless a big deal? Well, it had this polarization that is a perpendicular polarization that behaves like the one for the massless particle. But in addition, you have a longitudinal polarization. We call it epsilon L mu. And this longitudinal polarization is some vector that is along the direction of the momentum times 1 over the mass And here it goes like P0 times some, it's not P0, they call it P0 tilde. Okay. I'll not write it down. The important thing is that there's a polarization that satisfies epsilon square equal 1. You can have a unit norm polarization, and it's orthogonal to P. Sorry, I call it Q above. Sorry for the notation shift. Let me put that number here. Right. So you have a polarization. And the thing is that for a very relativistic particle, it's approximately equal to Q mu over M plus correction plus order M. Okay? So it's very strange. The polarization has norm 1, but its components are big because it's almost a null. It's not quite null, but it's almost null. It's a space-like, it's fine, it has norm 1, but it's almost null. So the fact that longitudinal polarization grow really makes the limit of a light massive particle very subtle. It doesn't smoothly go, in general, smoothly go to a massless particle with this polarization error. So there's two options. So when the thing's coupled to a conserved current, then what happens is that this longitudinal polarization essentially decouples, so you don't produce it. In this case, the longitudinal polarization decouples. So the probability that you produce it, it's sigma for producing it, it would be proportional, would be suppressed by this m term, proportional to some power of m squared over the energy scale you're looking at. So if you have a high energy process, the chance that you produce a longitudinal polarization is almost 0. And that's what happens in QED with a mass term. So sometimes you may read things in the literature that say that QED with a mass term is very different from QED because you have an extra polarization for the photon. But in fact, the phenomenology is almost the same because this extra degree freedom never thermalizes. Even in the early universe, if the mass is small enough, you just don't produce it. So these longitudinal polarization never reach thermal equilibrium with normal matter. Okay, so that's an important part of the phenomenology of this thing. Maybe I can mention the experimental constraint on the photon mass. You would think that the constraint on photon mass will come from this existence of longitudinal modes, but as I said, they're very hard to produce, and basically it doesn't come out. There's no constraint from that. The other thing that could constrain is the propagation across the universe, but this again is suppressed by the mass square. So if the mass is small, it's actually quite small effect. The main constraint, the main experimental constraint on the photon mass, they come from magnetic fields. Because if you have a large-scale magnetic field, the mass will damp it. So, and actually the largest magnetic field that we actually understand how they produced and we can measure is from the solar system. So we get something like a constraint like 10 to the minus 18 eV from solar system B fields. Okay, this number here is easy to understand. The Compton wavelength of a particle with this mass, 10 minus 18 eV, is about the distance to the sun. So, so if the photon and the mass that was comparable to the distance to the sun, would just mess up the magnetic field we get from the sun. Okay, it's a very basic constraint. You can try to get stronger constraints from galactic scale magnetic fields, but according to the particle data group analysis, you should not trust this constraint. They're much stronger, but they also are more uncertain because of we understand much less the production mechanism and the measurements. So yeah, so photon has to be light, but in principle, theoretically, it could have a small non-zero mass. Okay.
Are there any constraints from photon spheres around a black hole?
Well, they were not listed in the PDG, but I don't know. Maybe they will be. The question is, are they constraints from a photon sphere near a black hole? Yeah, I'm not sure. It would have to be that the dynamics, the detailed dynamics, is probing scales longer than that. So I'm not sure, but okay, maybe we'll see constraints in the future, but I'm not aware. Yeah. So the question. Okay. Okay. The other case is much more interesting. So in general, when you have a massive spinning particle, the thing it couples to is simply not conserved. So that's going to be case 2. Source is not conserved. So in this case, so remember that they assume that the longitudinal polarization is large. Q mu over m. It does not decouple. So the limit is not smooth, and you have 1 over m's everywhere in your amplitudes. Okay, when you scatter the longitudinal polarization. So one example of this is W boson in the standard model. It's basically the SU2 weak of the standard model if you don't have an Higgs particle. Then you have diagrams where the W's can interact with some Z or stuff. And suppose you put them all in longitudinal polarizations. What happens is that this amplitude for longitudinal polarization will have some 1 over m in the answer. And you'll get an amplitude that goes like some coupling for the weak force times S divided by m squared. So if you make the energy much larger than the W boson mass, this graph gives you things that grow with energy. Okay?
Without Higgs, W boson will not get a mass.
Oh, you can just add the mass by hand. And you can make it gauge invariant by adding the mass to be a nonlinear sigma model. So basically, this is the standard model without the Higgs. You have this picture of the Higgs potential as being something like this. And the standard model without the Higgs is something you imagine having a very steep potential. So if you imagine, if you make this potential very, very steep, then the Higgs becomes arbitrarily heavy and you lose it.
So it's the W boson without the Higgs boson, but with the Higgs mechanism.
Yeah. Well, I mean, if you make the Higgs mass very heavy.
But it's still eating the scalar that goes around the bottom.
Yeah. But the scalar is a bit, if you go to unitary gauge, for example, you don't have a scalar. The scalar is a bit of a choice of presentation thing. You could have a description where you have the scalar, they got hidden up by the massive W. But yeah, the invariant statement is you don't have the radial mode. The radial mode has infinite mass.
The Higgs boson.
Yeah, the Higgs boson is not there. Without Higgs boson. That's a more appropriate statement. Thanks.
Yeah, another thing, this is the same question roughly, but in the UV,
Yeah.
this would become a massless spin-one field.
Yeah, exactly. So it looks perfectly fine. However, you actually have these 1 over m term. So actually in the UV, this is not fine. And that has to do with the fact that by taking this linear sigma model for the Higgs and making the Higgs boson infinitely massive, you're making it into a nonlinear sigma model. And the nonlinear sigma model is not renormalizable. So the scattering of this W boson is related to scattering of the scalar in the nonlinear sigma model. And what happens is that, well, this grows, but an amplitude cannot grow. An amplitude is to be bounded because it's described a probability. So basically, we get a bound that new physics, if you study this theory literally without the Higgs boson, you need new physics below a scale which is parametrically the W mass. Apparently, the W mass divided by the coupling, okay, which is order the VEV of the putative Higgs. And so this was called, before the LHC was built, this was an important idea because this was a so-called no-lose theorem at LHC. Because this theorem sort of guaranteed that if you don't see a Higgs particle, you still have to see something. Okay. And actually, in this theorem, the actual numbers here matters, not just squiggly. People bother with the number, but I'm not going to quote it. Okay. Okay. Another example. But what you see from this is that the take-home message is that MW goes to 0 is not smooth. Okay, and that is actually the generic thing when you take a massive spinning particle and make it massless. The longitudinal modes do not decouple.
Sorry, could you explain again what's the issue with the M2 growing with S? Isn't this just the corrected S to the J scale?
The problem is that this is all in a zero spin partial wave, and the thing which are bounded, I think Sasha will discuss this a bit more also. Oops, taking a shock. The thing that is bounded is the scattering amplitude projected into partial wave of spin J, which is some integral over angle of m of s comma t equal minus 1 over cos theta times s. So if you integrate over angle, and you project the partial wave into angle, and there's a factor of 1 over s in front of that. Am I saying something wrong? Okay, we need to check the details, so we can discuss more after. I'm not completely convinced this formula is correct, but the statement I remember is that the spin zero partial wave does grow with energy, and that is ruled out. Yeah, let me put a question mark here about this formula. Okay, but the statement is that the m projected on j equals 0 grows with s. Okay. Yeah, no, I think it's just this S. That when you project to spin 0, you get that S basically out. Yeah. Okay, almost done. I want to say something about gravity. If you have massive, if you make the graviton slightly massive. So if you take Einstein-Hilbert plus a small mass term, now you can scatter gravitons that are longitudinal, or like doubly longitudinal, like in both indices. And now what you find is that this thing grows with energy very fast. So the massless limit of gravity is very not smooth, the so-called Weinstein discontinuity. And what you find is that this amplitude grows like the G Newton. And the best you can achieve, if you fine-tune the couplings to the best of your ability, the best you can achieve is something that goes like STU over M4. Let me call it MH for mass of the graviton. Okay. It grows very fast with energy. And against this arguments tell you that you need new physics before a scale which is of order, there's funny power. It's this G Newton is 1 over m Planck square, so the energy scale is like m Planck times mh square to the 1/3. Very funny power. This is called DRGT theory, the Ram-Gabadadze-Tolle. So the best you can achieve is that behavior. It needs a low cutoff. And the numbers are kind of funny. Like if you want a mass to have cosmological scales to be interesting for possibly some relation to cosmological constants or things like this. I'm not so sure about I never quite understood the motivation, but if you want to have a massive order cosmological scale, and you take this ratio, you get something that's like solar system size. So you just like There's a rich phenomenology of that. However, and so for a long time, this was the state of the art. You could say, okay, if you could live with this low cutoff, you could try to do phenomenology of this. And there's a very rich phenomenology of this. However, yeah. Yeah, so I would just finish in 1 minute approximately. Is that it turns out this is something that's been done like only 2 years ago. And that's going to draw me to my next topic of analysis and causality, is that this theory actually violates causality, relativistic causality, when energy is of order the mass of this graviton times something from order 1 number, or order 10 in this paper. So actually you get much stronger constraints on this type of modification by thinking carefully about causality type arguments that we'll go into next time. So effectively, this is a very great theory, but I think for many people, it is now okay. I'm not sure if the others fully agree, but there's more work to be done, but I think we're cornering it. Yeah. Thank you.